Hello, this is Greg Risteman from Olympus. I'd like to welcome everyone today to this webinar on the advantages of eddy current array over magnetic particle and penetrant testing for carbon steel surface inspection. In this webinar, we will review the new weld inspection solution and present results that demonstrate the solution's effectiveness for inspecting carbon steel welds. This presentation is technically advanced and is addressed to NDT operators and engineers. Our presenter today is Tommy Bourgeois. Tommy is a product manager for the Olympus eddy current testing and bond testing product lines. He has over 16 years of experience working to develop new eddy current and bond testing products and applications. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not used. If we are not able to get to your question during the live webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Tommy. Tommy, take it away.
All right, thank you, Greg. Hello, everybody. Thank you for attending this webinar. So today our agenda, briefly, will review shortly the industry problems leading to the development of that solution. We're going to talk about this Magnaform, that's the name of the product, the Magnaform solution, how it works, and as Greg mentioned, some results on various parts and applications to demonstrate the effectiveness. So, briefly, let's start with a recap on the current surface inspection method problems or known problems in the industry. Starting with the magnetic particle inspection, or MPI, basically it's the globally preferred method for inspecting carbon steel welds today. It's very good for surface breaking defects. The principle uses, basically, MPI uses strong magnetic field to magnetize the metal, so the particles attach to the discontinuities. That's pretty widely known. Anyway, I'm going to try to go fast on those slides a little bit, so I suppose this is known to most of you guys. The penetrant testing basically is an alternative on being mostly used on non-ferromagnetic surfaces or cases where the MPIs is more challenging. And it's also detecting only surface breaking defects. Principle, again, this is known stuff. The paint must be stripped and a thorough cleaning needs to be done before the inspection. And application of chemical waiting for the process is also needed. Okay, the paint removal is also significant because it needs to be removed before the inspection and also reapplied after the inspection. There are liability concerns from removing the paint because it exposes the bare metal, it's accelerating the corrosion, it could create contamination issues. Well, this is not the case for all applications, but it certainly is a concern for the most critical ones. So in a sense, the reliability is compromised from the inspection itself, from the paint removal. So playing with chemicals is also creating an environmental issue, which is basically a growing concern these days, as governments and agencies and companies are trying to get rid of chemicals for a greener process. Not to mention the cost of disposal, if done properly. This is a lot of chemicals needs to be employed, a lot of cans, a lot of quantity needs to be employed when using PT or MPI. The paint removal and the downtime caused by the inspection are often regarded because it is known that the direct cost of MP or PT is relatively low. So, however, the entire process, taking the paint removal and downtime, is a lot more costly than the inspection itself. Some additional limitations for MPI in particular, there's no depth sizing, no archiving. It's pretty tough to take a good picture of MPI, especially the wet mag. Multiple passes are required. False indications can appear on rough surfaces like the image on the right side, and not to mention the repeated effort from holding the yoke and reapplying the yoke on each and every place on the scanning pattern. So on the PT, specific to the penetrant testing side, what we refer to dirty cracks, or a crack that's been either previously inspected or has basically something in it, will prevent proper penetration from the die, so challenging to detect. And that's also true with SCC, stress corrosion cracking. If it's tight enough, if it's not really open and severe, it could be really challenging to detect with the penetrant testing, at least the visible form of it. So, as a summary, MPI and PT, they're very simple to use. That's going to be tough to beat how easy they are to use in the field. They can be applied to various parts or geometries. They're widely used. This is very well accepted. They're well suited for bare metal. So if the paint is removed, if it's ferromagnetic in particular, the MPI is the way to go. They have great sensitivity and resolution, especially the MPI provides a great image. The direct cost is affordable, definitely. However, when looking at the negative impact, while that explains why the industry is trying to replace those technologies and why you are so many attending this webinar, I suppose. The paint removal causing a lot of issues, the chemical issues, the bare metal and the liability, the downtime of the entire process, and the cost of it. The absence of sizing is certainly another issue. There's no easy archiving, so you have to trust the operator doing it and saying, yeah, it's been inspected and it's all right. So there's no proof, no data coming with that. Multiple passes are required. What ensures you that the scanning has been done properly? Again, it's the same trust that a company has to put in another company to do the job properly. The performance can be limited on tight or dirty cracks if it's the PT, and there's also potential for false indications and a lot of area for interpretation, especially on rough surfaces. All right, enough talked about the PT and MPI. Now it's time to talk about the Magnaform solution, what this makes it a distinctive solution for carbon steel weld inspection. First of all, this sensor or probe or solution can inspect through the paint, so it does not need to be removed. It's being tested heavily on paint thicknesses or shims very much because the paint does not affect the results. It's up to 3 millimeters thick without any problems. It's covering the entire weld surface. This is basically a 3 or 3.5 inches long sensor that covers everything, the heat affected zone, the toe, the crest, and crevices also in a single pass. And it maintains a similar detection everywhere. There's no more lift-off headache, so up to now, eddy current, because this is an eddy current-based sensor, eddy current has been somewhat challenging for inspecting welds because of the weld geometry causing lift-off issues. We're going to be talking about lift-off a little bit later on, but this sensor eliminates this problem because it's, first of all, it's a flexible array probe that maintains a pretty good contact, but not a perfect contact. But this is not the problem because there's also a software side that compensates dynamically the lift-off to correct the sensitivity. So it's a combination of both that makes it interesting. It's a very durable inspection. This magneform is very durable, has been drop tested and everything. We tested up to 22 kilometers scan before we noticed that, yeah, maybe it could be changed. The wear face could be changed. So 22 kilometers on actual steel on a test bench was pretty impressive. It's ready to inspect, can be fit into hand scanner or semi-automated scanners. So those are pictures of our most up-to-date scanners that we launched the last summer. And it's working well on pressure vessels or pipes or pipelines. There's also a motorized scanner that can handle this probe. This is accessible technology, affordable solution that works with the Omniscan MX flaw detector, and it's using a special software called the MXC Weld software derived from the commercial standard eddy current array software. It has also an interesting feature that we just added to allow the depth evaluation of a surface breaking defect. So the user can quickly evaluate the depth severity for screening purposes by selecting the defect and displaying the depth. All that comes with imaging. It's an instant interpretation because the instrument screen displays the image of the weld, okay? And you can archive those results easily by saving, producing reports, etc. on the instrument. Post-analysis is also possible. You can load the files, play with the data, and modify the setup if you really wanted to. You can do all sorts of things on the instrument. So how it works, we're going to focus a little bit on the probe to explain how that solution works. First of all, the basic elements. There's the actual cart called the magneform. So where's the magneform? That is the actual cart holding the probe. The probe is an eddy current array probe, so we're going to detail that in a few minutes. There's also a position encoder and a cable for that position encoder. So if we keep only the probe itself has a detachable connector. First in the industry, really, for a portable product having eddy current arrays in it, it's the first time that something detachable comes. It has a pre-shaped, what we call wedge, it's basically a plastic shape, and a sensitive face. So the wedge can be easily removed without the use of a tool in 4 easy steps. Basically, the sensitive or the wear face is employing Velcro that you can easily detach and slide the wedge off and put a new one in. Currently, we have 4 wedges that fits most pipes and vessels, and there's a flat, there's a large internal and external, and there's a smaller external wedge also. And the exact diameter do not need to be fit to the actual component because of all those the possibilities that the solution offers, such as the dynamic lift-off compensation. So the sensor itself, we're getting into more details of the sensors. It has a 16 plus 16 sensors, and there are 2 types. We're going to explain that. And it has active circuitry, amplifiers, and various things in the connector handle that makes that possible in a detachable format. And this is a picture at the lower screen that shows probably the closest to the actual sensor. I wanted this presentation to be accessible to all, so it explains a simplified version. If you want to know exactly how the sensors are done, you could ask the question, we could email you some additional presentation, but I'm not going to go in very much detail as far as how exactly electronically or physically the sensors are laid out. This is a simplified form of it. The sensors are using eddy current technology. Basically, the red lines display the lift-off, the distance between the coil to the actual part being tested. And this is possible because this eddy current is using magnetic coupling, and it's great for surface inspection. The benefits of eddy current: it inspects through the paint, it requires minimal surface preparation, it's suitable for metals including carbon steel, and it's certainly easy to use. This magniform sensor has two sensor types. The type 1, let's call that the crack detector, and the type 2 is a lift-off gauge. The type 1 sensor, this is an actual image from a patent application up there. Basically, it's a PCB equivalent to a cross-wound coil, for those familiar with that. It's ideal for carbon steel. This coil is certainly probably the best for carbon steel, and it's widely used in its non-PCB form, at least, in the weld ECT probe, such as weld scan, which is a name widely known. It easily detects surface breaking defects, and it detects through the paint, but it is also impacted by the liftoff. So that was type 1. The type 2 sensor is another eddy current sensor. Okay, it's PCB version of a sliding probe, for those familiar with it, and it's a stable liftoff measurement. And that's as far as I will go in terms of detailing the sensors. If you want more details, we will be happy to answer your questions or email you additional presentations. So back to the sensor types. The type 1 is combined with the type 2. So the crack detector and the liftoff measurement, they are combined in a new process called the dynamic liftoff compensation. And this is performed in order to have a compensated crack signal out of a raw crack signal and a liftoff measurement. It's dynamic because it is real-time software processing in the instrument. As you scan, you have dynamic liftoff compensation. It increases the sensitivity of the crack detectors when the liftoff is increased, as opposed to the opposite physical phenomenon. As example, if there is no or minimal liftoff, the gain is normal. But if there's more liftoff, there's more gain applied to the sensors. This is done to maintain a uniform sensitivity independently from the liftoff, and it's good because the liftoff is mainly produced by the weld geometry, which is certainly not very much predictable. Again, those sensors are independent, so imagine 16 independent crack detectors. Obviously, to simplify, I've laid out only 3 there on the screen. So they are overlapping. So there's also 16 independent liftoff sensors. And when they are combined, it produces 16 independent dynamic liftoff compensated channels. So if we apply that magniform scanner or probe on a weld, the actual probe sole or sensitive face is represented by the thick red line on the screen. So you can see it's being fit roughly to the weld surface, but not perfectly. In the toe of the weld, there is increased liftoff, and in the areas like in the heat-affected zone, the contact is perfect, but not everywhere. So what happens is basically the flexible probe takes care of the gross fitting of the probe to the weld, and the rest is done by the software. So if we represent the amount of liftoff by the icon I used, which is the ruler, okay? So small ruler means no liftoff or minimal. Big ruler means a lot more liftoff. Okay, so in areas in the toe of the weld, there's more liftoff. In areas where the contact is good, there's less liftoff. The crack detection is going to be the opposite. When there's less liftoff, there's more crack signal. When there's more liftoff, there's going to be a lot more or a lot less crack amplitude. So when combining both the liftoff and the crack signal, we obtain a reliable compensated crack signal. And this is what is displayed on the instrument screen, is only the compensated signal. The representation uses live impedance plane, which has been introduced in the latest embodiment of MHC of the eddy current array equipment. It's basically, we're watching the vertical amplitude and displaying that into the C-scan image. That C-scan image is representing basically a 2D mapping of the scan. It's displaying the indications according to the vertical amplitude and a color palette, so you could change or customize this. And the two axes, one is called the index axis. This is the actual coverage of the probe, 3 inches or so. The other axis is the scan axis, being typically the distance, and could also be the time if you wanted to. So, is sizing possible? Quick example. If we use various depth or defects, surface defects, 0.5, 1, 2, 3 millimeters deep, it's widely known that the depth of the surface breaking defects has a direct effect on the amplitude when using eddy current sensors. However, it's not that easy because there are other variables impacting the amplitude. The liftoff, which has been a concern for so many years, the magnetic permeability of the part itself, and the defect length or shape. So, how about the toe of the weld as an example? If we use the probe profile as before, and we put a 3 millimeter defect, not in the heat affected zone, but right at the toe of the weld, basically, because of the added liftoff, we could expect a reduced sensitivity. So I picked an example where a 3 millimeter defect typically looks like a 1 millimeter defect or so because of the added liftoff and the decreased sensitivity. That is before Magneform was introduced, and dynamic liftoff compensation corrected this because the dynamically compensated sensor helps fixing this sizing issue in order to retrieve an amplitude that is very similar to the defect being scanned without additional liftoff. Because of that, the depth evaluation is possible. So how that works, basically the user or operator would pause the instrument and use the selection cursors. And right after selecting the defect, a sizing display, the depth is displayed on the top left of the screen with a millimeters or inches reading. So while doing that, the length of the flaw is actually being taken into account in the sizing algorithm in order to compensate for shorter defects or longer defects in order to get a more accurate sizing. Now it's time to talk about the results on various parts. I've picked the most relevant examples, mostly weld inspection results, but also some stress corrosion cracking results at the end. For the results were highly interesting. So I hope you don't mind the extra results on this presentation. Okay, starting with a painted pipe, carbon steel pipe, 6.5 inches. The wall thickness is about 1/2 inch. Paint thickness was made very thick, actually two applications, just to push the limit a little bit of the tool. Machine flaws were used in and around the weld, so they were made using EDM process, and all the sizes were measured for comparison purposes. The weld has 4 fillets on the top, and it's carving approximately 1 inch in most places. The surface is certainly rough. The surface of the weld itself was rough. However, obviously it's painted. So this is a scan made with the simple cart. The representation, basically, again, this is the index axis or the coverage of the probe, and the other axis is the because that was a pipe. This is a circumferential axis, or the 360 degrees. In brighter shade, you can see the heat affected zone. in the middle, this is the weld area. And obviously all those indications are the various defects placed along the weld in the heat affected zone, crevices, toe, center, all areas of the weld. And what the screen shows is it can work through paint, it can detect with a relatively uniform sensitivity the same type of flaw everywhere. Another example here, a painted coupon with a little bit smaller dimensions where the thickness is 3/8 of an inch or 9 to 10 millimeter. The paint thickness 3/1000 of inch, and the flaws were also induced here. So 3 flaws. One is a defect in the toe, linear defect, easily detected. One is transverse, and the porosity actually was not detected. This tool is not great for the porosity. It's very good on cracks, but the porosity still needs to be done with a visual examination. We pushed the limit and created an additional sample requiring a extra roughness on the actual weld. So we went with a 12 inches or so plate, ½ inch thick, no paint, but there's a protective varnish on it, which is 2 to 3 thousandths of inch thick. The flaws were induced by a special process while welding. There are flaws everywhere, including the undercut. And again, this weld has been very rough with, I hope the image can convey that. They had to use a buffer to smooth the weld on some areas, but they didn't care to make it very smooth. They really went quickly there to preserve the roughness, so we could really challenge the tool. There's 4, again, this is a 4 filler passes, probably 1.5 inches thick weld. The drawing, I hope you can see something on the drawing. There are some 10 millimeters, 15 millimeters, and 25 millimeters long defects pretty much everywhere and in the undercut. So the next screen, I have some detection results. There's a center line crack, 10 millimeter. There's a crack in the toe, 10 mm. There's another crack in the toe, 15 millimeter. And the lower string defects are also detailed. There's a crack in the undercut itself that is still detected. And there's a couple dimension cracks there. And the undercut itself doesn't, this one has been performed a little bit, this one is a little bit severe, but it does not show the red shades there. Another challenging aspect is detecting longer defects. That's been relatively tough to do with eddy current up to date. This is an example with carbon steel plate, 3/4 of an inch thick, with a large radius. There's no paint. That's because it's been previously removed through MPI, and there's the presence of a continued long crack in the toe. This is a mag particle scan of the exterior and interior, and this is the magniform scan of the exterior, showing the defects on each side of the weld, and this is the interior of the weld, same thing. Otherwise, this screen would have been pretty much white or gray. Now, some examples with stress corrosion cracking. This is a 1/4 inch thick pipe. There's no paint because it's been removed previously to do the PT. The actual SCC has been marked by hand. That's me marking with a Sharpie where the SCC was, so I could take a picture for comparison purposes. So that on the left, there's a picture of the actual marks where it's been, and you can actually see the cracks into the Sharpie marks, and the SCC results on the right side from the magniform. So we pushed the limit a little bit. We went on denser stress corrosion cracking, and this has been very challenging to detect on with using PT. I think pretty much this plate is full of SCC everywhere. You'll see a magnetic particle scan after. The PT has been revealing only one track, and without any further ado, here's a wet mag results. Okay, those are localized pictures, but of course you can imagine the entire surface is pretty much the same. And this is some one of those areas being scanned with the magniform, revealing pretty much everything, including distinction between the depth of the most severe colonies. Now, that's nice, but if you add corrosion to this whole picture, this is another example where of a pipe that's been heavily corroded. We removed the paint to be able to sandblast it and add EDM, or electro-discharge machining defects inside and outside the corrosion areas to be able to compare with and without corrosion. The results are pretty interesting. Obviously, the EDM defects are well detected when they are outside the corrosion, but what is the most interesting fact here is that the lower screen on the right basically would typically show as bright red because of the added corrosion, but right now the magniform, because it cancels the liftoff or dynamically compensates it, was able to detect that EDM in one of the worst corroded areas. Yeah, I forgot this animation. So the corroded areas were tamed or reduced, significantly reduced from the dynamic liftoff compensation. So as a conclusion, this tool can inspect through the paint, has the dynamic liftoff compensation as the main driving force for obtaining all those results. A single pass is needed to cover a weld and not multiple passes anymore. It can do well in stress corrosion tracking, even in the most challenging applications such as corroded pipes. It can evaluate the depth. The word evaluation is important. This is not a precise depth sizing, but an evaluation, so more as a screening purposes. So if more advanced sizing is needed, something like UT can be used. And certainly is a great tool, magniform is a great tool to have the imaging and the archiving capability. So I hope you enjoyed this webinar. Again, as Greg mentioned, it is recorded and it's going to be posted on the Olympus-IMS website, so you can watch it again with the audio. I could see in the comments that some people lost the audio. Hopefully we recorded everything and it's going to be posted. Again, we're going to scroll through all of your questions and answer them separately by email. There seem to be a sheer amount of questions that's going to be better dealt with by email. Again, thank you very much. We appreciate you attending this webinar, taking some time at your office to watch this webinar. Thank you very much for attending.
On behalf of Olympus, I'd like to thank all the attendees for joining us today and Tommy for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar, along with a Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event will receive a follow-up email, whether you attended or not. And that follow-up email will have links to the archived presentation so that you can listen to it again. That's going to do it for today. I want to thank you again for attending, and we'll see you again next time for the Olympus webinars.